Cool. So, welcome. So last time we were talking about current and resistance, and we introduced the idea that current is the amount of charge per second that flows down, for example, a wire. And so it's measured in coulombs per second, which is termed the amp or the ampere. And then we did some calculations, and we said, look, maybe we can get an expression for how quickly the charge carriers move. That is their velocity, not their instantaneous speed, but the velocity with which they move, which is the displacement over time. What we find is actually, although the speed is very quick, the displacement is actually quite small, measured in actually millimeters per second. And we could do it like this, bringing this term drift velocity and figuring stuff out. It depends upon the number of charge carriers per unit volume, which is the material, and the charge on a charge carrier, and the cross-sectional area of the wire, and the current and the like. We introduced this idea about current density, and I've got to be honest, in most of my life, I've not used current density that much. We talk in terms of current voltage and resistance. We'll talk lesser about resistivity. So current density is useful for getting, deriving things, but it's not something that you'll be using an awful lot. I don't believe. Certainly I did not. So if the current is number of charge carriers per unit time, the current density will be the number of charge carriers per unit time crossing unit area. So fair enough. And this kind of leads us, we can talk about the current density equals the conductivity multiplied by electric field. And again, that's not one that I tend to deal with so much. We do talk about conductivity, but we kind of talk about it mainly as the inverse of resistance. So in deriving it, they go through conductivity, but I think, once you get to resistance, that's the figure of merit you tend to use. And basically we get this idea that, okay, well, we have this thing called resistivity. Well, resistance for a sample, resistivity for a material. And we end up with Ohm's law. And this is, you're going to use Ohm's law over and over again, which says that the EMF, or the potential difference, if it's the power source, it's called an EMF. If it is the effect of that power source across that component, it's called the potential difference. And you can think of it as a water pressure and water flowing through. That's a good analogy. But the potential difference is equal to the current flowing through that component times the resistance of that component. So V equals IR. Okay, what do you control? You control the resistance because you pick the resistor and you put it in the circuit. And you control the voltage because you set the power supply up. You picked it or you set it. And the circuit responds with the current. So we'd say that the current is a dependent variable. It depends on what you do. Whereas the voltage is a independent variable. It's what you set. You go to the machine and say, 5 or 7 or 9 volts. So typically when we plot graphs out, we plot the independent variable along the horizontal because you're setting that. And then you plot the dependent variable, the answer, if you like, on the y-axis. And so when we plot this, I's vertical and V's horizontal, and we get a straight line. For a nice resistor, we will get a straight line. That's not always the case. If you took an old filament type light bulb and you turned up the voltage on it, you'd find that the current would not be linear because there's a heating effect taking place. There's a heating effect with resistors, but not so much. It's not so extreme. So what we find is that for a nice resistor, it's a nice linear relationship. But here's the rub, and this is what catches people sometimes. They'll go, oh, it's linear, so V equals IR, so the slope is the resistance. And skipping the fact that this is V equals IR implies that the horizontal thing V equals IR. I being the vertical thing. I being the horizontal thing, I'm sorry. So when I look at this, the equation, the equation that I've plotted here involves I is equal to V delta V, if you like, over R. That's that relationship. So my slope is 1 over R times delta V. Yeah? So my slope is 1 over R. But in this case, what I plotted to get this to work out would be delta V and I. And then my slope would be equal R. So just watch out for that. It just can catch you up sometimes where you look at your graph and go, oh yeah, the resistance is such and such, but you've swapped the axes. So is that clear? Yeah, okay. So a sample has a resistance. So a sample has a resistance. A material has a resistivity. And that's a bit like, if I think about it, and it's ironic because it's the same symbols, but if I want to talk about the density of a material versus its mass, yeah? It's the mass of a sample of the material, but the density of the material. So we might say aluminum has a certain density, but an aluminum block has a definite mass. So one's about the material and one's about the sample. In the same way, we can talk about resistivity of a material, and we can talk about the resistance of a sample of that material. And this resistivity, well, the sample is measured in, the resistance is measured in ohms, and the resistivity is measured in ohms meters. So this is ohm meter. Ohm, and that seems like a weird unit, but we'll get to that in a minute. Resistivity is 1 over the conductivity. So a nice insulator, that's got a big resistivity, is a poor conductor. So ceramic would be a big resistivity. It means it's a poor conductor. Aluminum is a good conductor, so low resistivity, that kind of thing. Yeah. So the unit of resistivity is the ohm meter. So that should be ohm meter, yeah. If we take a material and we put it into a uniform shape, so just the same cross-sectional area. This is a circular, this is like a cylinder, but it wouldn't make much difference if it was a square, as long as it was a nice uniform shape. Nice. It doesn't bulge or get... If I had something that kind of looked like that, I'm not sure this equation would apply anymore. If it was a tetrahedron, if it was some kind of weird shape, you couldn't really apply this. But for this, there's an obvious L, and there's an obvious A, and it's not changing. So then we get the R equals rho L over A, so my resistance is equal to my resistivity times the length of the resistor material over the cross-sectional area of the resistive material. So let's do one of these. What is the resistivity of a cylindrical resistor that is made of a material that's a resistivity? Oh, and so here, I'm sorry, I need to correct this. This is ohm meter, and I do it I do it throughout, so it's ohm meter. Resistivity is not in ohms per meter, it's ohm meter. So what we say is R is equal to rho L over A. So this is going to be my resistivity of 4. I'm in SI units, ohm meters, so I don't need to worry about that. And my length is 3. and my area. So here I'm giving you a little bit of a curve. So it's, oh no, I'm not actually. I've got it in standard units. So that's 0.2. So that's going to be 12 over 0.2, which is 60, I think, 60 ohms. Now, just put yourself in my shoes. I'm giving you this as a test question. I don't want it to be, just plug and chug. So what can I do to make sure you're thinking? What can I do? What would you do if you were me to make it a... So I could give you the radius. And then that tests, do you also know that pi r squared equals the area? So I'm checking on that. I'm also checking, are you reading? Are you just looking for numbers and plugging them in? Are you actually reading? So that would be a little wrinkle. I can do something a bit more... no, I probably wouldn't do that, actually. But I could, I suppose. I never thought about that. That's a good idea. No, all these come up for the following semester. So then what else can I do that you've seen before? You've seen me do this. I'm really keen on the fact that you don't make mistakes when you're doing this kind of thing. Yeah, I could give you it in, square centimeters or something like that. Just stuff like that. And of course, I can ask you for different things. So. 6 ohm resistor, what is the resistance of so here's another skill. So what we just talked about was the same skill, just dressed up a little bit. But here's another skill. So a resistor has a resistance of 6 ohms. So that's the standard symbol for a resistor. There's an international symbol which is that, and you'll see both of them kicking around in circuits. But let's use the standard symbol, the US symbol, and that's going to be 6 ohms. And what is the resistance of another resistor that is twice the resistivity, its length is tripled, and its cross-sectional area is halved? So here's another resistor, but I don't know what the resistance is. And the first thing to do is you look and see what's in the question. So want to know the resistance, I'm given a resistivity, I'm given a length, I'm given a cross-sectional area. So it's to jog your brain cells and go, R is equal to rho L over A. And I'm trying to find resistance, so I'll leave it like that. And then you recognize, but hold on, I don't have any base units. I've just got changes, ratios. Then you say, okay, and this is the standard technique. You say R new over R old. And this is a bit that people sometimes skip on. And it's really, they make mistakes. Look at what your R old is and put it in immediately. And then I look at my expression and I'm going to go resistivity new times length new over area new over resistivity old, length old, over area old. Now, I'm looking back up here and I say, well, I don't know what the resistivity is, and I don't know what it was, but I know it's twice as much now. Its resistivity is doubled. I know it's twice as much now. So I just simply say, oh, well, this number here must be twice as big as that number there, and the easiest ratio is 2 to 1. Then I say, well, what about its length? Its length is tripled. Okay, I don't know what it used to be, and I don't know what it is, but now I know it's 3 times longer than it used to be, so the easiest ratio is 3 to 1. And its cross-sectional area is halved. So I don't know what it is, and I don't know what it used to be, but I know it's now half as much. So that means it's 6 over a half, which equals 12. And I can't tell you how many students have got to this stage and then give me, well, it's going to be 12 ohms, which is not the answer. So you're going to say, well, Rn over 6 is equal to 12. So Rn is equal to 12 times 6, which equals 72. It's going to be ohms. And it's such a shame when you get to that stage, and I think basically it's layout issue. It's that people, they tend to over-focus on the numbers. So if you're giving me that bit, and none of this, then I'm having, first of all, to interpret what your numbers stand for. And then secondly, because you're not writing in complete sentences, you're not expressing a real thought, you're expressing a phrase. And so you then forget about the fact that you were given 6 ohms because it's not part of your phrase. And then at the end you say, oh, well, 3 newtons is equal to something, like it's a sentence all of a sudden. So really try and break yourself of that habit. Okay, try and write in complete sentences, and you'll make fewer slips like that. And it's such a pity because you know how to do it basically, but you just, your bridge is going to fall down because of a slip. So try not to do that. Okay. We're going to do a model for electrical conduction, and again, I'll tell you what's important and what's not important. So you assume that a conductor is a rectangular array. So I'm going to draw one plane of it, but it's like this whole set of atoms all nicely on a square matrix, And we say, assume that the conductor is a rectangular array of atoms plus a collection of free electrons. So let's go here. Let's have my electrons. Oh, interesting. Okay. Let's go here. Color. Let's go green electrons, as we know. So we have some electrons whizzing around. And in the absence of electric field, the conduction electrons move randomly through the conductor. And by the way, they have speeds of about 10 to the 6 meters per second squared. They're moving randomly. That's the key thing. They're moving very fast. Under all circumstances, they move very fast. But they're moving randomly. So the one might be going in that direction, and down here one might be moving in that direction, and one might be moving in that direction, but over here one's moving in that direction. And then one's moving in that direction, and one's moving in that direction. So there's no net transport. It's like a crowded room. Everybody's kind of like blindfolded, and they're just walking around. It's a big room, so they don't bump into each other, but they're just going in all directions. There's no net motion of the people. In the presence of an electric field, then the conduction electrons still move randomly, but also drift in the direction that is opposed to the electric field. So, wish I'd not done colors anymore, but I did, so I'll just continue with it. So ink color is red, and we'll have our array. But now we have a nice electric field superimposed on this, and we have our. And what happens is that these guys, they arc because of the electric field. The electric field is pointing upwards in this case, but they arc. They're electrons. And this guy arcs. And this guy arcs. And this guy arcs. So there's a drift. The tendency is, although you're going up for a while, the tendency is you'll eventually be stopped and turned round, and you'll move in that direction. And so, although there's no net velocity in that direction, in that case, there is a net velocity in this case. It is much smaller than the actual speed of the electrons. The electrons are going at a tremendous speed, 1,000 kilometers per second. They're going at a tremendous speed. But what happens is, they'll basically hit into things, or they'll basically have numerous collisions, and they'll slow down. So in the presence of an electric field, the conduction electrons still move randomly, but also drift in the direction. What that means is they're still being bounced upwards, but they drift. They're still being fired downwards, but they drift. So on collision, there's no predictable direction the electron will go in. You collide, you're going to come off in some direction. So it's not a nice linear thing. So they randomly, but also drift in the direction that is opposed to the electric field. And the drift velocity is really small, 10 to the minus 4 meters per second for typical values for current and the like that we use. 10 to the minus 4. The conduction electrons gain energy between collisions, but lose energy during collisions. The energy given up during the collision causes temperature of the conductor to rise. Yes?
That is in the case of the drift, right? That is in the case there's an electric field.
Yeah.
Because in the other case, there's still collisions, but there's no rising heat.
Oh, and I have no good answer for that.
Okay.
Because I just don't. Because you're perfectly right. There is, I mean, you know, if you take this rectilinear paths, then they're going to hit something. And I don't, the only thing it could be is the difference between an elastic and an inelastic collision, but this is an electrostatic field, so I have no idea why that's not the case, because what he's saying is basically, hey, there's collisions even when there's no electric field, so why doesn't the temperature of a piece of wire just there get hot? If it's getting hot in a resistor because of the collisions, which is what I've said, then why doesn't a piece of wire get hot?
That's
And
like chemistry stuff right there.
so I don't know. I just don't know. So I'll think about it, and I'll tell next semester's class. You know. So that's the advantage of being a teacher over many years. You kind of like you learn every semester, and by end of 10 years, you kind of know what you're doing. You know. So. A model for electric conductivity, this is the analytical version, and I don't, frankly, let's not get bogged down on this, but basically we're taking our force, which is our charge times our electric field, and F equals ma, and we're combining them. And that gives us an acceleration, and I can use acceleration in my kinetic equations, just substitute in. And then what I say is, well, okay, I can have this, I can invent this time. And this is the time between collisions, on average. How long is it between collisions? Let's just call it a time constant. We're going to do that a lot in different things. And then we say, well, we have an expression for our current density, so we'll bung that in. And so we get an expression for our conductivity, and so that gives us our resistivity. And I don't really care about it. Okay, so know the equations exist. If I give you the expressions, know that t is the time between collisions. So I'm saying don't remember it for the test, but don't just blow it off and don't remember it at all, because I'm not above just showing you that equation and saying, hey, this is the equation for such and such. What does this mean? And just seeing if you know it. It's a nice, easy point for me, and it kind of tells me whether you're studying your notes, so watch out for that. This next thing kind of comes out of experiment, I think. If you change the, so here's the idea. So when I went to college, I learned to play foosball, table football, yeah. And you know, there's like 4 lines per team, isn't there? So one person is the defense, and the other person is the attacker, and then you know. It goes on like that. And, you know, in my college, my dorm, there was a foosball table. And, you know, the way our college worked is there were 25 people to a kitchen. And there's a mixture of second-year people and first-year people. So you don't know anybody when you arrive, but half the kitchen knows each other. So there's like the ins and the outs. And human nature being what it is, when the new people arrive, the second years want to act really, you know, established, and you know they form a club and exclude you, kind of thing. And then after a while they realise that you're okay, or maybe they just don't have a third person to play foosball. So they say, hey, come on, Bonaquisti, why don't you come down and play foosball with us? And you're keen to get on with people because you want to make friends. So you say, okay, so you go and play with them. And you've never seen a foosball table before. And so you're on defense, and as soon as they get the ball, they score, and as soon as they get the ball, they score, as soon as they get the ball, they score. And first, the opposing people are kind of gleeful. They still ridicule you a bit, but they're gleeful about it. And they start making these false compliments to you, like, you're a really good player, I'm glad you're on their side, and stuff like that. And then your teammate, of course, turns on you and starts asparaging your breeding and your family and your skills and all that. And then in desperation you start, and you realize, because you're a physics person, you realize that the problem is that the goal is that big, and my little guy is only that wide, and so there's all this. I got two more guys here, and they're only that wide, and the ball comes through and scores. But if I can just nudge it, I save a goal. So the trick is you don't have to stop it. You don't have to have that thing in the middle of the ball path, even if you just touch it. So man, if I only could have a bigger paddle, a bigger person. And you realize there's a certain length of time that this thing takes to pass your guy. And so if I can, during that length of time, move this guy sideways, so in my delta t, I move that guy from there to there, my paddle is now that big. And so somewhat instinctively, you just start, as soon as they get the ball, you just start oscillating these two guys backwards and forwards. And all of a sudden, you are golden because no one's scoring, because between these guys, you're covering the goal. And and it stops. And you're running out of breath, but suddenly your teammate likes you. And these two guys give you kind of begrudging compliments, and you think, I've made friends, I've established myself, I am now well respected. And then on the way back to the kitchen, they start talking about Sicilian defenses, because of course I'm Italian, so of course, well, I'm not Italian, I'm Sicilian. You know, anybody with an Italian name is Sicilian in Britain, because they're so unusual. It's the only region of Italy they probably know, you know. And they say, oh, and they start giving you an Italian nickname, which is like, oh, come on, you know. So you realize they're still second years, and, you know, they're not really your friends. But I got over it. It's okay. I'm just talking about it 40 years later. So here's the thing. When something is moving around, it covers a larger area in a given time. And so imagine that you have a wire and it's got atoms that are not particularly moving. We can look from this end and we can say, well, out of that cross-sectional area, there was an atom there, an atom there, an atom there, an atom there, an atom there. But if I have the same number of atoms and they are moving, I've drawn it a bit extreme, but as I look from there, I look at this same area, I see, oh, look, there's much more area covered by these atoms. So it's called a cross-sectional effect. You've increased the cross-sectional area of the atoms because of their motion. And that's what happens when you heat something up. It starts vibrating, the atoms start vibrating, and so they have a larger cross-sectional area, apparently. And so as you're the electron trying to wend your way down the wire, you basically are more likely to have a collision. And so based on the idea that the more collisions, the more temperature, the more energy exchange, the bigger the temperature rise, then I would expect a temperature effect for resistivity or resistance. So this is the example of resistivity, and this is the example of resistance. It's the same equation. It's just using resistivity rather than resistance. It's a linear equation. It doesn't look it. It's a bit of a complicated form for it, but it's a linear equation. And materials will have a linear temperature coefficient of resistivity or temperature coefficient of resistance over a certain range of temperatures. And so it's kind of useful to know if you have a circuit and it's going to get hot, how will that affect your resistivities, resistances, because that's going to affect the operation of your circuit. So I didn't have any of the answers on this. So this is ohm meter again. Shame on me, ohm meter. And we say a material is a resistivity. So we have an example of a material. And our resistivity is equal to 4 ohm meter. And it's 20 degrees C. And the same material has a resistivity of 9 ohm meter, and it's going to be 30 degrees C. So what's the coefficient of resistivity? So I say, well, what did that equation say? My resistivity is equal to my resistivity at 0 modified by 1. Is it minus or plus? T minus T. Did I get that even close? It's plus. It's plus. Oh, I forgot my alpha, didn't I? My alpha's there, isn't it? Yeah, so I kind of know it. I need to brush it up, don't I? So I say my resistivity 4 is equal. Oh, let's not do that. So you've got to decide which is which on this. And T0 is the one temperature, and rho 0 is the other temperature. And that's usually taken at 20 degrees. So this would be rho 0, and this would be T0. So we'd say, okay, 9 is equal to 4, 1 plus 30 minus 20. Alpha, I've got my alpha again. 9 is equal to 4 plus 40 alpha. So 5 is equal to 40 alpha. So alpha is equal to 5 over 40, which equals 1 over 8, which equals 1.2. Is that good, right? 8 goes into 1.025? 125? Okay. Oh, yeah, that's right, 0.125, sorry. And what the unit's going to be?
It's just a coefficient, so it's like just...
Yeah, that's just... So it's going to be rho over rho naught. And then that's temperature times 1 over T. Oh, degree C to the minus 1. Go. Just by the by, I just never thought about this, but let's just deliberately put it in the wrong way around and see what happens. So I'm going to say 4 is equal to 9, 1 plus alpha, 20 minus 30. So I'm deliberately messing it up. I'm doing it backwards and seeing minus 5 is equal to minus 40 alpha. So it works out either way, doesn't it? So alpha is equal to 40 minus 40 over minus 5, which is the same. So it actually doesn't matter if you get those the wrong way round. It doesn't matter. Okay. I'm sorry?
You have to get both of them wrong.
Well, 9 goes to the other side, becomes minus 5.
Right, divided by the bottom one.
Oh, yeah, sorry. Yeah, apart from the math. Yeah, I was right, yeah. Sorry. I jumped to the answer and then the working was just for the sake of it, yeah. Bad mistake. Cool. Okay, bit of a change. Electrical power. A battery converts chemical energy into electrical energy. Electrical energy lost by the battery is converted into other forms in the circuit's components. So a 10-volt battery provides 10 joules of energy per coulomb. And that's an important thing, I think, to remember. If you get a 1.5 volt battery, you need a lot of coulombs to transfer a certain amount of energy. But if you have a 9 volt battery, you need less coulombs. So it's kind of like, hey, lower current gives me as much energy. So it kind of makes sense. If during an experiment 4 coulombs of charge passes through a simple circuit before returning to the 6 volt battery, then 24 joules of energy was dissipated in the circuit. So what I'd say is, let's try and formalize this. I can say my potential difference is equal to my energy per coulomb, energy per charge. Didn't we know that before? Isn't that what we've learned in the potential stuff? Electric field, voltage equals... well, anyway, there it is. I'm thinking about something fresh and I don't have time to think about it. So, potential difference. So I want you to click in your answer for this. Might as well. I'll write the answers in. Just give me a second. Potential difference of a 6 volt is dropped across the resistor. How much energy is converted to thermal energy when 8 coulombs of charge passes? So multiple choice, what you do is you add the two of them together, so that's 14. You take the two of them apart, that's going to be 2. You multiply the two of them, that's going to be 48. And you divide them, that's going to be 1.33. Then you get your units right, so you say, well, this is going to be joules, 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 joules. So what's it going to be? So what do you think? You've got 3 people. Come on. Come on. Come on. Think of what voltage is. We just said it. Break it down into its basic units and then think of what charge is. And then say, oh, how can I get joules as my answer? I'm going to stop you in a few seconds. Okay. I can find my cursor. I'll stop you in a few seconds. There we go. Stop. Let's see what people are saying. Most people are saying C, and that is the answer. Let's just go through this again. So basically, this is awkward because there's not really an equation we've written down for it. We're actually using definitions. But we just said that our potential difference is equal to joules per coulomb, how many joules of energy per coulomb of charge that flows. And I want to get joules in the end, and the other thing I have is my charge is in coulombs. So if I say, oh, my potential difference, let's say delta V, multiplied by my charge is going to equal my energy. So I'm going to say simply, it's going to be 6 volts multiplied by 8 coulombs. Each coulomb delivers 6 joules of energy, so I end up with 48 joules for that. Cool? So, cool. Last little bit. And this is another thing that's just it tends not to be answered so well, and that is that the rate of energy dissipated, that's expended, is termed electrical power, the time rate. So power equals my energy per time, and the amount of energy is my charge multiplied by my potential difference times time, divided by time. And so I can see that, well, I have charge divided by time, which is current. So I learned as a student, I learned watts equals volts times amps. And you just learn it. P equals I delta V. And then there's various versions of this. We have delta V is equal to IR. That's Ohm's law. So I can get, well, P equals IV, but if I substitute in to get rid of delta V, I have I squared R. And if I substitute in to get rid of the I get V squared over R. So these are 3 equations. I know this one really, 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 really well. It's kind of in my DNA now. And I know that one really, 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 really well. And I know these other 2 exist. So when I'm doing a whole bunch of homework on these things, I can remember these other 2. But most of the time, I just go, oh, yeah, I just got to convert. It's no big deal. Okay? So let's do one. Current of 6 amps flows through a 5 ohm resistor. So let's just do that. So this is I is equal to 6 amps, and it's flowing through a 5 ohm resistor. What power is dissipated? How much energy per second? is given off, and I would say power is equal to IV, which equals 6 times 5, which equals 30, and because we're in SI units, I know that is watt. Boom, boom, boom. We dealt with power in Physics 1. We did it, work per second is equal to power, and then the energy converted is equal to power, yeah? And we had a bit of an issue sometimes, because when I asked people for the energy in a given time, they would stumble. So let's just say, sorry? What is it? Everybody's got their hand up. Oh, I am so asleep. Shame on me.
I'll help you be as forgiving to us.
No, absolutely not. I will erase this tape, though. So delta V is equal to IR. So let's have a look. I have an I have an R, and I have an A, so I want to get rid of my delta V. So I is equal to IR. So that's going to be I squared R, which equals 6 squared times 5, which equals 360 divided by 2, which is 180, I think. Can you just check on that? And it's going to be watts. Okay. Can you determine for me, please, find energy dissipated in 2 minutes? And I'm going to give you various answers. I'm going to go, A is going to equal 90 joules, B is equal to 360 joules, C is going to equal, let's have a look, 3 joules, in 2 minutes, I'm sorry. Yeah, 3 joules, no, 1.5 joules, and D is equal to 180 times 120, whatever that works out to be joules. Oh, I have my calculator in my pocket. I didn't click it open, did I? Oh, and then E is equal to, let's have a look, this is going to be 1.27 times 10 to the minus 8 joules.
So the power that's dissipated is different than the wattage.
So it's the energy that's dissipated.
So
I'm asking for energy.
I understand.
Power that's dissipated is wattage.
Oh.
It's energy per second. So are you referring to the use of the term dissipated?
Well, I'm referring to the difference between joules and watts.
Oh, so joules is just how much is delivered, and watts is how much is delivered in a certain amount of time, per unit time, basically. That raises an interesting point. Let's just, I'm going to give you just a couple more seconds. That raises an interesting point that we've got to talk about. Yes?
You also, in the previous slide, say energy dissipation is called power, electrical power.
I'll get a look back at that. Well, let's look back at that now. So I'm saying the rate of energy dissipation.
Okay.
Yeah, so rate meaning time rate. Yeah. So while we were just watching this go through, let me say, so my brother's an electrical engineer, and it kind of razzes me every now and then because we talk about things in different ways. And a lot of it I put down to just the fact that he has a different vocabulary because he's an electrical engineer who works with motors, so he tends to use different terminologies that are not commonly used in physics textbooks. But frankly, after a while, you realize it's more than that. He actually views motors in a different way than I view motors. He's got a much deeper understanding of motors. So whereas I get, oh yeah, it's a magnetic thing, you know, it's been forced, magnetic force. He's kind of got much deeper feeling about it. So he has much clearer insights into how motors work than I do. But one day he said to me, well, you guys only think about, well, he says, you guys focus on energy, whereas engineers in general focus on power. And I said, really? And he said, yeah. He goes, it's like this. And he goes, this is the problem with what you do. You keep asking, is it possible? And we keep saying, when is it possible? And he said, so the analogy is, somebody comes to you and says, I want you to build a pyramid for me. Can you do it? And your answer is yes. Because, of course, you can do it. It might take you 5 generations, but you can do it. When they mean, can you do it in the next 2 years? An engineer will say, when do you need it for? Because it's when can you do it? So it doesn't matter if you can do it. Yeah, I can walk to, well, I can't walk to Australia, but I can walk and swim to Australia, but not realistically. But in principle, I can. But, you know, realistically, I couldn't do it in my lifetime. You know, I could not literally do it in my lifetime because I know how fast I swim. I couldn't do it. But the and that's just that difference in, and it's a really, I think it's a really telling difference between the physics tradition and the engineering tradition. I think yes.
So for determining units, we just view watts as just joules over second.
Watt is a joule a second. Yes, they should not have named it after watt. It's just one of those named units that hides the physics of it. Yes, that's exactly right. So what do we get on this? Are we still? So stop it and look. And most people are saying D, which is, yeah, it's the right answer. It is, so the, so energy equals the power times the time. And so that equals the power, which is 180, times the time, which is 120. Yeah, so there it is, yes. Cool. I think that's it for that section, yes. So let's end it there. Let's take a 5-minute break.